This talk is building fast ClickHouse analytics for MySQL transaction data using Kubernetes. So we'll be talking about MySQL, we'll be talking about ClickHouse, and we'll be talking about Kubernetes and how we're tying these things together. Oh, and we're off to the races. Okay, so one of the things I want to say up front is that this is pretty new work. It's based on an open source project that we're doing right now for a Kafka sync connector to ClickHouse. So it's at a stage where we want to begin talking about it, showing people what we're doing, the problem we're solving, and then invite people to come and check it out if they're interested. I'm Robert Hodges, and I have with me today Kanthi Subramanian. And just some introduction. So Kanthi is an open source contributor. We both work for Altinity. And so he's got a great data engineering background, and he is one of our developer advocates. I'm a database geek. I've been working with databases for about 40 years. And my day job, when I'm not doing stuff like this, is I'm CEO of Altinity. Just a little bit about Altinity. So we are specialists in ClickHouse and analytic applications. We've been around for 5 years. So have a couple hundred customers, wide range of applications that we've worked on or helped people work on. We do a lot of work in Kubernetes. That's one of our, pretty much a specialty of the company for the last 4 years. We wrote the Kubernetes operator for ClickHouse. We built a cloud on top of that operator that now runs with getting up to 100 customers on Amazon and GCP. And we just announced a new feature where we can actually have that cloud connect to people's private Kubernetes and manage ClickHouse there. So we are really into data and data, ClickHouse, and Kubernetes. So let's jump in. So just very briefly, I think most people here know that, you guys all are database people. You understand why you want to do real-time analytics. Really common, this is just a common use case, e-commerce. People are doing transactions on a website. They want to ask questions like, hey, what's the rate of return for special offers? There are people, as you probably know, that spend their life figuring questions out like that. And there's also a lot of people who are very interested in things like, hey, does this transaction look fraudulent? Do I need to call it back? So the classic way to solve this is standard architectures. You've got your upstream data sources, which are generating data associated with digital transactions. So either people putting something in a basket or buying something along with just the web server logs as they're traversing pages. These things get fed into an event stream and then pumped into a data warehouse. And then they feed various downstream applications like analytic dashboards and fraud detection. So by data warehouse, what we mean is a database that is designed or can do very efficient reads on very large amounts of data. We'll talk more about that in just a second. So with ClickHouse, and I'll talk just a little bit about ClickHouse in a second because not everybody's heard about it or knows about it. Generally speaking, in these pipelines, you'll have something like the following. So you'll have MySQL upstream. You may have many of them. There's various ways to do change data capture from MySQL, but a very good one these days is Debezium. It is widely used for MySQL based in Java. Also has adapters for Postgres, MongoDB, other databases. So this is something that we're leaning on in this project. The event streams tend to be something that's either Kafka or something Kafka compatible. So we're going to focus today on Red Panda. It's a Kafka compatible event stream that's just mega fast. It's very efficient C++ implementation and can move a huge amount of data very quickly. At the far end, sort of downstream, we have ClickHouse, low latency data warehouse. And then the question mark here is how to make that jump from the event stream into ClickHouse. This is something that is still even today not well served and that we're trying to solve. So let's see. Oh.
Next one?
Oh yeah, next one.
Right.
Oh, sorry. So ClickHouse, SQL Data Warehouse. So how many people here know about ClickHouse? All right, a few. All right. I think of it as, you all know MySQL, right? How many people know Vertica? Okay. data warehouse, very, very famous, started by Mike Stonebreaker and friends. ClickHouse is kind of like MySQL combined with Vertica, in the sense that it understands SQL, runs on bare metal, it's open source. Those are all good things for MySQL. ClickHouse can actually run on, believe it or not, on an Android phone. There was a blog article about that a while back. So those are the, sort of the things from the MySQL side of the house. From Vertica, which is pioneering data warehouse, we get things like columnar storage. We get a shared nothing architecture where you have a bunch of nodes connected on a network with attached storage. We're gradually moving that to be separated, but that's another story. And then incredibly efficient parallel execution. So vectorized on individual nodes, so the ability to read these columns, split them up into pieces, dispatch them onto all the available cores, use SIMD instructions to process them quickly, and then run in parallel across many, many nodes. And it's becoming a hugely popular engine for real-time analytics. The project is enormous out on GitHub. It has about 400 contributors a year, which is very, very large, bigger than Elastic. Okay, next. All right, so without digging deeply into the architecture, with ClickHouse and any data warehouse, particularly one that allows you to distribute data across a lot of nodes, there's some good things and there are some bad things. So these are trade-offs, right? So, so the good things about ClickHouse, it's incredibly fast. So you can read, 1 trillion rows of data. If you have a cluster correctly configured, you can load it in a couple hours. If I load anything less than 2 million rows a second, I think I'm doing something bad. So it handles very large amounts of data. The original developers, Yandex, have about 100 trillion rows in their clusters. There are many larger clusters than that now. So it's very, very scalable. It also does incredibly efficient aggregation. So aggregation, averages, sums, looking for uniques, things like that. Those are really important. And the best thing is that, query on ClickHouse, if your data is there and you're querying it and pounding away, it doesn't affect your operational stores, and that's really important. This does come at some cost. ClickHouse has limited support for transactions. They are not particularly important in databases that are largely write-only. It just turns out that if you're not messing with the data a lot, failures are not that common. So it doesn't have a full ACID model. We are working on that, and there's a support for that coming in, but this is something that you have to be very careful about. Another thing is that you must batch the inserted data. Because we have columnar storage, to write a row, if you have 100 columns in your table, you're going to write at least 200 files. So, yes? There's isolation in the sense that when you write blocks, which are kind of like ClickHouse does have a transaction model. We write parts, which are chunks of data that compose tables. And when those are written, they are atomic and they're fully isolated in the sense that you'll never see dirty blocks. But there's no notion of, hey, like set isolation level or do MVCC or anything like that. There's nothing like that in ClickHouse. What can happen is you can see things in inconsistent states, and that sounds terrible if you're kind of a Jim Gray person. But in fact, we're dealing with a distributed system here, and things are always inconsistent. So ClickHouse kind of leans on eventual consistency in a big way. So, yeah. No. ClickHouse is eventually consistent, and yeah, I want to be totally upfront about that. And the final thing is, because of this, along with this update and delete are hard, and we'll get to a very specific example of that in a minute. And I think it's time to turn it over to you, Kanthi.
Oh, can you guys hear me? Okay. All right, so it's not like a Zoom call where I can kind of exit the call and walk away. All right, so my background, I've been doing this for about 20 years. Data engineering for the last 5 years. I'm an open source contributor to Airflow, a little bit to Cassandra, We'll be actually at ApacheCon. I think it's going to be a fun meetup to meet other open source contributors. So yeah, I've been at Altinity for a month and a half. This is a month and a half work, so it's still a work in progress. But it doesn't seem to break for now, so it's good. Actually, yeah. So we talked a little bit about this architecture. So our objective is to get data from MySQL all the way to ClickHouse. And there's already a few technologies that's doing that. So we'll just go through what the existing technologies are, and pros and cons, and why we actually spend time and effort to develop a new one. So the first one is, you guys can hear me, right? All right. Materialized MySQL is actually built into ClickHouse. So it's good in a sense that as on the operational side, you don't have to set up like 3 other components. It reads bin logs directly from MySQL. So you pretty much in the configuration, you give the MySQL information. It has support for updates and deletes, but it's still experimental. So I'll talk about that in the con. So the con for updates and deletes are, the way it does it is it has 2 columns called the sign and the version column. The sign column tells you if it's an update or a delete. So I think if it's a -1, it's a delete. The version is more like a current flag, so it gives you the state of the row. And it uses what's called a collapsing merge tree, which is a background process in ClickHouse. So for example, if you have 100 rows with modifications, ClickHouse picks the last version and pretty much deletes everything else. We have more slides to talk about that. The unfortunate thing is it stores this last version information in a local file, so it doesn't support replicas or shards. The other biggest con is when you set up replication from a database, it unfortunately replicates all tables, so you can't really pick a specific table. The next one is the blog aggregator by eBay. This is just amazing. You got to read through the presentation and the slides. They've solved the problem of exactly one semantics and deduplication. So the pro is it solves exactly one semantics, which is to make sure that one record from Kafka is inserted to your sink only once. So it's exactly once. It's not at least once, so there's a big difference. It supports replicas and shards. It uses the ClickHouse native protocol, which is actually faster. So that's kind of what the driver is. The ClickHouse driver is based on native protocol. And it supports Kafka rebalancing. They actually have another process that maintains the partition and offsets when Kafka rebalances partition and offset information, which is really cool. The cons are they only kind of talk about half of the pipeline. They don't really, there's nothing to get data from MySQL. It's only a tool to get data from Kafka into ClickHouse. It's kind of difficult to extend because it was actually written in C++ using librd Kafka. There's not a lot of configuration. So that's kind of a con for me, maybe not for everyone. It doesn't support Avro and schema registry. So we find in our benchmarking test that Avro makes a big difference compared to JSON. And schema registry also makes a big difference in the throughput because you're not actually including the schema in the payload. The schema is actually in this separate schema registry. You're only including the version in the payload. So when schema evolves, which happens all the time, people delete columns, add columns without letting us know, and the pipeline breaks. And so schema registry is useful. So you can go click on this evolve schema button. The last one's Kafka engine. This is also built into ClickHouse. Again, the cool thing is there's no extra setup required. You don't have to run additional processes. But again, just like the eBay solution, it's only for getting messages from Kafka into ClickHouse. But the good thing is it reads directly from Kafka. The cons are it supports at least one semantics. I'll actually get to that in one of the slides we talk about exactly once. And the message must be written to Kafka in ClickHouse compatible format. Yeah, so we'll cover this in the data type mapping slides because there's a lot of work that needs to be done to transform your records from MySQL data types into ClickHouse data types. So that's a huge part that's missing in the solution. Any questions? Keep going. Okay. All right, so our objectives, and we work closely with the client who is very big on performance. So yeah, performance, throughput, CPU memory usage is definitely our key objectives. No data loss, duplication of records. So because we have these different components, we have the source connector, which actually uses Debezium. We have Kafka. We have the sync connector, and then we have ClickHouse. All these components can go down. So you need to have high availability, and then it has to be fault tolerant. It has to have some sort of some sort of way to get back if it fails and comes up. So the exactly one semantics is also a very critical requirement for us. Transaction support. This is actually something not a lot of other sync connectors do, and we'll talk about this in detail in the other slides. So we actually read the MySQL transactions, and we have a way to write it as a block into ClickHouse. The updates and deletes, we have a solution for that, which is pretty much similar to what the materialized MySQL does. Schema evolution, because we support Avro, and we tested with the open source Apicurio schema registry. So that's out of the box. All right, so this is kind of a slide that talks about the current state. So we tested using JSON records in Avro. We have a feature of deduplication using primary key. That dedupe is primarily because Debezium can introduce duplicates, because the source connector can go down and come up again, and we could have duplicates of those same CDC events, and that's why we had to build this. The exactly one semantics, transaction support, inserts out of the box, native Kubernetes support. We're big on Kubernetes. Our Altinity cloud is on Kubernetes, so we want this end-to-end to work on Kubernetes. And the other big thing is, compared to the other solutions, our connector can support multiple topics. I mean, it's kind of easy to say you're going to have one process that supports one table on one topic, but then in an environment where you have like 1,000 tables, you're going to run thousands of these connectors, which is not very good in an operational perspective. So we have configuration that lets user set up these different topics in one connector. All right, so this is kind of the architecture. Does anybody know about Kafka's Connect SDK? Okay, I'm going to assume that's a no. So if you look at the blog aggregator, which was just a C++ Kafka consumer, we could have done that too, but the Kafka Connect SDK gives a lot of benefits of actually scaling your consumers based on the partition and topics load. It also gives in custom converters to convert your source data into different formats like protobuf, JSON, Avro, and also gives support for schema registry. So yeah, so that's kind of a statement on why we went with Kafka Connect SDK. So our solution sits on top of Kafka Connect, and then so the first component is ingester. So it's pretty much like a Kafka consumer .consume where you get the records. The only difference is you get what is called a sync record. So based on what you specify on the source side, if it's a JSON or an Avro, you would get messages in that format. So the ingester pretty much gets all those records, passes it into a deduplicator, which holds a buffer for deduplicating records, passes it on to the converter. So this is where we map the data types from MySQL to ClickHouse. So we'll talk about that in detail, but for example, datetime is one of the examples where the MySQL datetime range is longer, but the ClickHouse is shorter, so we have to limit it. And sometimes maybe it's useful just for a user to store it as string, so we kind of give that flexibility. So after it converts it from the Kafka Connect data type into ClickHouse, we have our own kind of model or schema for the data. We push it into blocks, and this is so blocks are just a collection of records. And so the idea is ClickHouse merge trees are not optimized for doing frequent inserts. There's a latency with doing frequent inserts, so it's much more performant when you're doing bulk inserts. But that size of the block and the time the block is flushed is configurable by the user. I think we set it to 10 seconds by default. So the converter sends it to the other component, which creates the blocks. And then we have this other background thread. So like in web applications, it's very similar. Your consumer thread is very much similar to your web application thread. You don't want to block that. You want to make sure your processing is done outside of that. So that was the idea, to have this background thread, which pretty much reads these shared blocks and flushes to ClickHouse. One thing to note is we use the JDBC library, which reads the blocks and does a bulk insert into ClickHouse.
Can you parallelize?
I mean, that's the thing we haven't got into, but one thing we're kind of leveraging is the parallelizing aspect of Kafka consumers, because async itself, so you can actually define the number of tasks in Kafka Connect. And if you have, let's say you have 3 partitions and 3 topics. One task can handle one topic in multiple partitions. So you can just keep growing the number of tasks.
On the source side.
Oh, on the Debezium side? On the Debezium side, yes, it's impossible to parallelize it, because I think it reads the bin log in sequence. But if you actually set up partitions on the source connector side, the source connector will write it as partitions on the Kafka broker, and then we can parallelly read it from different partitions. So there's parallelism in that way.
One interesting property is that, I mean, we haven't really dug into this too deeply. We could probably read the bin log and parallelize it. I'll show you why in a second when we get to the insert and the next question.
Okay. this is not exactly in place now, but the idea is we so the idea is we're going to have a buffer with for a primary key, and then we pretty much check for every incoming record if that record is already there. If it's already there, we just drop the record. As simple as that. But the part where it gets a little bit difficult is because we handle multiple tables from the source side, we obviously want to make sure that the primary key is associated with the table. So we're going to have different buffers with the topic name and the partition name as the key. All right. So the exactly one semantics. So this is the problem that the block aggregator talks about in detail. Maybe it's easier just if I just look at this. So as I said before, we get everything as sync records. The sync records have the bin log, the actual name of the bin log, and the position of the bin log. So it's kind of useful if you're looking at end-to-end to kind of figure out what's the CDC or what statement changed on the MySQL and how it's written into ClickHouse. So yeah, as we talked about before, we write everything into blocks, and so the block size of the block is configurable by the user. So it's this part of writing to ClickHouse is where we want to make sure that only one record is persisted. So there are two steps in this process. So out of the box, going back, step one is you obviously have to flush the records into the block. Step two is you have to let Kafka know that I've successfully processed a block. Now move the offset from, let's say example 0 to 1000. You have to acknowledge, actually Pulsar has a nice .acknowledge function. Kafka, it's automatic. So you have to let Kafka know that we have successfully processed 1000 records. Now move your marker to 1000, so that we can read records from 1000 onwards. These two have to be atomic. Anything can go wrong. So one of the thing with Kafka engine and why it's not exactly once is because they actually write the offset to Kafka first, and then they push the block to ClickHouse. And so there could be scenarios where you write the offset, but then the data is not in ClickHouse. So you're going to get the data again, and you're going to process it into ClickHouse again. With the block aggregator, yeah. Yeah, so we do the exact same thing. We do a different. First is we make sure we do a bulk insert. So if you look at the bulk insert, it's kind of guaranteed that it's going to be written fully. There will never be like half-written records. So it's guaranteed that it's going to be written fully. Everything in the block will either be written or not persisted. So that part is guaranteed with the bulk insert functionality of ClickHouse. So going back, we kind of do it the other way. We actually, so we store the offset in the ClickHouse table. So that's kind of different from what blog aggregator does. Instead of the blog aggregator stores it in Kafka topics. So again, Kafka can, there could be Kafka rebalancing. We could lose the partition offset. So that's one reason we decided to store the actual offset into a separate ClickHouse table. And then we make a bulk insert. So the worst thing that, so for example, the first step fails, cool. It's nice because we haven't told Kafka that it has to move the offset, so we're safe. The worst thing is we go back to whatever is stored in ClickHouse and we start again. So first step of offset is done. Second step of writing to the actual payload to ClickHouse fails. Okay, that is covered by, again, using the ClickHouse bulk insert and the deduplication mechanism that's part of ClickHouse. So they have something called the merge tree, which is an engine, and we'll talk about that later. But if you pass to ClickHouse a block of records in the same order, ClickHouse would deduplicate it. But it's kind of a background engine. It's more like a JVM that runs in the background and deduplicates the record. So that's how we guarantee step 1 and step 2 is atomic. The other reason we're doing this is there is work going on in ClickHouse to support transactions, but unfortunately right now there's no way to support transactions when you write to different tables. But we predict that it'll be there sometime soon, and then we can actually wrap this up in a transaction and write it to ClickHouse. Yeah.
The PR went in, but it says experimental, and I think they need it.
All right. Yeah.
Re-import the same batch twice, it's going to be deduplicated. But if I import one block first, another block next, and the same block as the first block,
It will be deduped. What ClickHouse does is this was developed originally for replication, where you could, be pushing something to one replica, somebody dies, and you go switch to another replica. So what ClickHouse does is it maintains a table of hashes. The blocks are generated the same way, and we're big on sorting, for example. So it's very easy to generate blocks. And ClickHouse will see, hey, I've seen this hash before. Sort of way. So it's really it's part of example of how in these large distributed systems you begin to think about transactions in a different way. And fundamentally, the way ClickHouse deals with it is rather than figure out whether we did it before, just do it again and throw it away. That's what we've seen.
and when you say it does from the background, so you wouldn't do it. It's not necessarily immediate that you will do it.
What you'll get is you'll just get an acknowledgement, and you don't really know what happened. ClickHouse does the right thing.
All right.
It doesn't say, hey, you screwed up. It's like, and what this does is it means that you can have these very, like, when you're loading data warehouses, you do not want to be thinking about, just constantly error checking. So if you just want to jam the data as fast as you can, if it doesn't work, jam again. And that's
You
how you
use
get
that
started.
as a mechanism to write the payload on the other table because ClickHouse will take care of the implementation of the data.
Yes.
Makes sense.
Okay. Time's running fast. So we're one of the few sync connectors that actually support transactions. The reason is because Debezium introduced support for transaction, I think, sometime last year. So on the source connector, you have to enable a flag for Debezium source to write that transaction metadata. Unfortunately, the current implementation is the transactions are written in a separate topic called the transaction topic, and the payload goes into a separate topic. So on our sync connector side, we're actually mapping the transaction and the payload by bin log, file name, and position. And our implementation is we make sure that all the records in the transaction go into one block. So that it gets inserted as a block into ClickHouse. But when we have transaction support in ClickHouse, we'll change that to use transactions. All right, I think that's it.
Getting some deletes. this is an interesting topic, but can you guys hear me? Yeah, I'll make it quick. So updates and deletes. So it's really easy to insert stuff in ClickHouse, and it's optimized to do that fast. In a relational database like MySQL or Postgres, you're pretty familiar with, you insert a couple rows, you maybe delete one, you maybe change the last one. And this is really easy to do because all the data is in one place, and MySQL is optimized to do this quickly. You can't do this very easily in a data warehouse, especially when the data are distributed across nodes. So we have to think about data in a different way. So let's go to the next page. So what you want to do is, and why is it hard? I mean, if you want to delete a row, so you don't have a guarantee that when you're touching ClickHouse that you're necessarily, as you ask for something to be deleted, that you're necessarily even looking at the same node where it was inserted. If you have to make that guarantee, then you're starting to build a lot of coordination into your apps. So instead, we tend to think of things, if we can, as turn the update and delete problem into an insert. And then, just insert all the things that we want to have happen, and then have a process to resolve what the actual appearance of the data is. This is a classic way of handling this problem in distributed systems. So for example, as Kanthi mentioned, in the there's already implementations out there that use what's called replacing merge tree. There's a couple of different engines. There's another one called collapsing merge tree. The basic idea is that when you insert data, fine, you just throw it in, and you have a assign column, which says, +1 means, hey, I'm adding something, and then you have a version column, which is just monotonically increasing. When you delete something, you would say -1. And as long as you have the same key, what's going to happen in this replacing merge tree table is eventually it'll get around to saying, hey, I've got two guys with the same key. It's the last one that I need to keep, and it will collapse it. So, and you can force the collapsing will happen by itself in the background in general, although it's not completely guaranteed because sometimes these records could be spread across multiple nodes and they don't know about each other. But you can let ClickHouse do this collapsing by itself, or you can actually force it in a query. So this is the basic idea then, that you will see you'll see these signs, sort of 1 to add, -1 to take away, and then the monotonically increasing version. As long as you can get the data and sort it, you can figure out what the current state of the database is. It has some interesting effects. So when you use this approach, and this is a subject of great discussion right now to think about what's the, what is the right way to do this. First of all, when you do selects in ClickHouse, if you're actually fetching data, you have this final keyword, which means it says when we're doing the query, go ahead and resolve all these rows that need to be collapsed so that we'll see a consistent view of the data. This is expensive to do because it means we have to fetch all the data and sort of run it through a sort before we can do things like aggregation on it, because otherwise we'll have extra copies. So, oh, you got a question? No, you don't. There's no rewriting. Oh, when you collapse. Oh, thank you. Thank you. Yeah, excellent question. What happens is ClickHouse does a background merge, and it will take the blocks and it will compare them, and as it's merging two blocks in this merge process, it will recognize, hey, I've got two values for this same key. I'm going to keep the one with the highest version number. So interesting, if you don't want to pay the expense of that, then you actually have to do your aggregates a little bit differently. If you want to count rows, what you'll do is you'll say select sum of those signs, and that will give you an accurate count. Similar kind of deal with averages. Not all aggregates can do this, so there are some downsides to this approach. But these are ways that allow you to deal with update and delete at very large scale with data that's spread across multiple nodes. One thing I want to say is this sounds, if you're just seeing this for the first time, it sounds terrifying. Here's an interesting thought experiment. This scheme will allow you to read the bin log out of order. So why is that? Because we can generate a version from the bin log offset that we're on, or the GTID. And what that means is we could just read random pieces of the bin log and insert them into ClickHouse. And as long as we, get most of the pieces, at any time we can do an insert. And because of this sorting property with the version, we can actually read the bin log. We can actually see the correct state of the bin log. So going to that, who has had the question about reading out of order in the bin log? Yeah, reading in parallel, exactly, which means out of order if you don't have coordination, you can do it. So this is sort of, you begin to think about data in different ways with this, and we are basically building a system that is designed to work not for millions of rows, for billions or even trillions of rows. And that's why we're so interested in this. Oh, go for it.
Yeah, so this is kind of what that converter we showed in the earlier picture does. It's what maps. So because we're using the Kafka Connect SDK, we don't know anything about MySQL data types. It actually comes in Kafka Connect or Debezium data types. But yeah, so the work that the converter does is it converts all the Kafka Connect data types into ClickHouse data types. And one good example is the date time. In MySQL, it starts from 01 to 2100, but ClickHouse only supports from 1970. So we have a configurable parameter. Either we kind of truncate it to or set it to those limits, or we just write it as a string so that the users can query it later. All right, that's it. Oh, we're going to talk about this.
Everybody here knows what Kubernetes is, right? We're just going to skip this part. We're going to skip to the pipeline, and then we can do a demo.
All right.
Yeah, so these are just very quickly, because I think the demo is the cool part. We want to get to that. This is what the pipeline looks like. And I want to say up front, this looks complicated. And yes, it is. And part of our goal right now is just to get all the pieces working together, and then we're going to automate the bejesus out of it. So, but these are the pieces that you can put together. We have all of these things documented and working in the project. There's, with Kubernetes, there's one of the things that is kind of an issue in Kubernetes is when you have these multi-part or multi-component systems, they have different ways of installing. You could run a script, you could do a Helm chart, or you could install an operator and then use a custom resource definition on it. So our goal is to figure out what the right approaches are, and then over time we will iron out what the the steps that you have to go through to get this to work automatically. We're at the stage of just getting the pipeline to work.
All right. Demo time. Oops. Okay, so I'll briefly just show. Man, it's too big. Damn it. Okay. So one of the problem with with Kafka Connect is if you need to add new connectors, you have to use a REST API. So your connector comes up, and then say you want to add this ClickHouse sync connector, or if you want to add, I don't know, a Snowflake sync connector, you actually have to send, actually I have that request here somewhere. Yeah. So yeah, so you have to say, this is kind of the JSON payload of how it works. So you curl and you send this payload, and then your connector starts up. So yeah, unfortunately, this wouldn't work in a place where you have 1,000 tables. You can be doing 1,000 curl REST API calls. So we use Strimzy. So Strimzy is a CRD, or say an operator implementation of of most of the components of Kafka. They're part of the CNCF. So you could, so Strimzi has, you can actually bring up your entire Kafka broker on Kubernetes. You can write your consumers. You can create topics. So they have something called the topic operator, and they also support Kafka Connect. So this is how a manifest looks like. I mean, it looks exactly like a Kubernetes manifest, except that it uses these CRDs. So the first step, if you're installing this on a brand new cluster, you want to make sure you install the Strimzi CRDs. And they, the other thing to note is they have two concepts of Kafka Connect and Kafka Connector. A Kafka Connect kind of maps into, say, a pod. And then a Kafka Connector would be kind of, say, applications that's spread onto a pod. So if you want 10 topics on a pod, then you would have one Kafka Connect, and then define all these 10 topics in your Kafka Connector configuration. So you can actually specify your topics. This is actually another cool feature is by default, so for example, you have employees and products in MySQL. You want to map that to employees and products in ClickHouse. It's easy. By default, it does it. But in real life scenario, you want employees to map into something called employees_dated. So we have this option where you can actually specify, okay, what topics go into what ClickHouse tables. The other ones are standard. This is actually another useful. So we actually store the Kafka metadata objects. This resolution is messed up. So we actually store, for every row, we store the partition, the timestamp. So we didn't have time to build that Grafana dashboard, but then we get a lot of useful information to figure out lag. We actually get the timestamp of the source, so the time when the MySQL record was actually inserted, the timestamp when it was processed by Kafka, the timestamp of when we write it into ClickHouse. So you can actually calculate the lag between source and ClickHouse insertion time, Kafka consume and insertion time. So it's pretty useful. And then we also store bin log, position, row, server ID, server thread. And these are, again, configurable. The raw data is kind of a lineage or like useful in audit purposes. We convert the entire row into JSON and we just write it to a different column. Other useful, sorry, you were going to say something?
I could say one thing on that. The converting this into JSON, it sounds like kind of trivial and not interesting, but in fact what it does is it means you've got this blob which has all the data for the whole row. So one of the things you can do is now you can basically, we support Bloom filters, so you can do the equivalent of full text indexing on these rows. And this is another example about how we're thinking about, you know, you think like, hey, you want mirror image mappings, but actually if you want to get analytic information out of this data, being able to explode it out into these other forms, which maybe show the whole history, maybe, you know, show the data as lumps that you can then do the equivalent of full text indexing on. These are all things that enable you then to do better analytics. So I just want to, because I've seen applications that do this and it's kind of mind-boggling how well it works if it's correctly tuned.
Yeah, that's.
Yeah, but it takes away the Bloom filter, which is really like, yeah, I'm conflicted.
Yeah, I think ClickHouse has really cool JSON functions for querying JSON when it's stored as a string. So you can, yeah, query by keys and also the JSON for each row. So yeah, I'm just going to skip. Everything is documented. There's actually steps about how you can install all these different components on Kubernetes. We don't have a Helm chart for now. We'll have that sometime soon. You see all these, that's my little Python process trying to insert data. So this is just a demo of, so we have a MySQL database running. Okay. Yeah, I'll just finish off this. And then, so we have the entire pipeline set up. I just didn't want to do it like with the demo because it takes a while to set up Red Panda Certificate Manager. But the idea is we have this Grafana dashboard where you can actually see information about the block. You will see that one block could have records from different tables and topics and tables and partitions. So we try to capture that in this dashboard. So that's easier for troubleshooting. I still have to change the graph type. It doesn't look awesome, but just an example of how we support different tables. And so you'll actually see that this is ClickHouse. This is the employees table. It actually maps from the employees pre-data table. And then, damn it, where is that? Yeah, so we haven't really tuned the compression, but the product table is 64K compared to about 256K in MySQL. Right, I think that's about it. Anything else you wanted to add to the demo?
No, I think that's it.
We will work on the dashboard and update more lag because that's kind of our way of testing it out and making sure the lag is minimum.
Yeah. If we could just show the last slide, just where to get this project and while it's coming up. So bringing this back up to the top, our goal here is so you're seeing a lot of the pieces here. But as I say, this has reached a state where we feel like it's important to talk about it and start telling people what we're doing. So this is the roadmap. But the basic idea here is that we think, like as a business, we're really big on delivering open source data management sort of data pipelines that lead to ClickHouse, this Apache a licensed server. And so the idea here is that we believe that the entire data pipeline should be open source, freely usable, and for any business purpose in any location. And so this piece was missing. That's why we're putting it in. But as we optimize the pipeline, we'll continue to inject more stuff into open source so that this stuff is usable. And then what we do as a business is we actually build the management on top of it. But if you don't want to use it, hey, no big deal. If you don't mind setting up stuff with Helm charts, great. Come do it. If you're interested in contributing to this project, we would gladly work with you. This is something that is beneficial to the entire community. And what we want as an endpoint is to have the ability to you have data, valuable data in MySQL and other databases. We want to make it, in the end, as easy as possible to get it into an analytic database and be able to answer interesting questions about it. And you're seeing kind of version 0.1 of that effort.
Yeah, one cool thing is the last one. You can, the auto scaling using Kata. So I don't know if you guys know Kata. It's a Kubernetes autoscaler. So Strimzi implements the scale functionality of Kubernetes. So the way it works is you can scale your Kafka connectors based on lag metrics, which is really cool. So if your consumer lag is big, and so real life scenario, right? I mean, you're going to have a lot of load in a retail company during the day. So you want to have, like, say, 10 pods, but then you want to scale down in the evening. Or someone on the source side adds another table without letting you know. So this auto scaling is really cool. Like it'll spin up. You can obviously specify a max, but we'll have a demo next time. I think that's it. Oh, thank you, Paige.